we have got is a binary phase diagram. A binary phase diagram refers to the situation when we are dealing with two elements. And in this example here, as you can see in this phase diagram, we have got copper in here on the left, and we've got nickel on the right. So at the extremity of the left side of the phase diagram, we have got copper, 100% copper and no nickel. On the other extremity on the right, we have got 100% of nickel and 0% of copper. And in between, we have got an alloy of the two participating elements, starting with, say, 10%, starting from, say, just slightly more than 0% of nickel. As we move from left to right, the nickel content of the alloy increases, and then eventually we reach to 100% nickel. Well, and right here, as you can see down here, we have got a single solid phase, and that is alpha. Below this solid use line, we have only a single phase, and that is alpha. Above this liquid use line, we have got only a single phase, and that is liquid. And in between, in this region, we have got solid alpha plus L, which stands for liquid. So two different phases of liquid and solid coexist in this region in between the two curves that are solid use and liquid use. Well, and as we can see, we can have a unique, say, crystalline structure or solid for any combination of nickel and copper, because some properties of the two elements are similar. Say, for example, they have got same crystalline structure, similar atomic radii, and also similar electronegativities, making it possible for the two to be combined to one another at any proportion. So any combination results in the same, say, single crystalline structure of alpha. Now, let's see what problem is asking us. A copper-nickel alloy of composition 70 weight% nickel and 30 weight% copper is slowly heated from a temperature of 1300 degrees C. So composition is given. Composition is, say, 70% right here, and temperature is also given, which is 1300. So it brings us to somewhere here. And then we want to see at what temperature does the first liquid phase form. Well, if we heat it up from this temperature going up, we keep going up until it intersects the solid use line right here. At this point, the first drop of the liquid phase appears. So I'm going to move on to the next slide here so that there is a better representation. That's the point I was talking about right here. If we extend it to the vertical axis on the left, then it gives us this temperature. So at this temperature, the first drop of the liquid phase appears because the alloy is entering into the two-phase region where we can have liquid and solid present at the same time. And then the part B of the question, what is the composition of this liquid phase? In order to find the composition of this liquid phase, what we need to do is, say, to actually draw a tie line here and find the intersection of this tie line, which is a horizontal line, with curve of solid use, which is right here. And then bring it down here, which comes to, say, I didn't do it properly, but anyway, if we do it properly, it comes to this figure of 59 weight%. This figure, if we project it down, it comes to 59 weight% of nickel. So the first drop of liquid phase appears when temperature is 1345 degrees C and its composition is only 59% of nickel, which is less than the overall composition of the alloy that was 70% of nickel. Part C, at what temperature does the complete melting of the alloy occur? Well, in order to at what temperature does the complete melting of the alloy occur? What we need to do is to elevate temperature. If we do that, then it brings us to this point right here, this point, and the temperature at this point when we are going just to leave the two-phase region right here. Then the required temperature at this point is 1380 degrees, and in part it is asking us what is the composition of the last remaining solid prior to complete melting. To answer this question, again, what we need to do is to draw a tie line here, a horizontal line, and find the intersection of this horizontal line with the solid use line, which is this point, right? This point. And then bring it down, which is giving us a composition of 79 weight% of nickel. So to conclude, what happens is that if we start heating up the say alloy from 1300 with a composition of 70%, then the first drop of the liquid phase appears at 1345 degrees. Its composition is 59 weight% nickel. Then if we continue this path and heating it up, then complete melting happens right here at this point, because above this liquid line we will have only a single phase, and that is liquid. So complete melting is resulted at the temperature of 1380 degrees, and its composition, if we take draw a tie line, horizontal line, find the intersection with solid use and bring it down, we get the composition of the solid phase, the last particle of the solid phase, which is 79 weight% of nickel. So the first drop had less atoms of nickel in it, so it had only 59 weight% of nickel, and the last particle of solid, which was still in place, was richer in nickel, and that had 79 weight% of nickel. Why is this? Because the atoms of nickel have got a higher melting point, which is right here, compared to atoms of, say, copper, which is below 1100 degrees C. So when melting begins, more of the atoms of copper move from the solid phase into the liquid phase. And what is resulted is that the remaining amount of the solid phase will be richer in nickel, richer and richer. However, the overall composition still remains the same, and that is 70% of nickel. Okay, moving on. Is there any question on this? Okay, no questions. So if there is no question, we will be continuing the activity. Okay, in problem 1, is it possible to have a copper-silver alloy of composition of 58% silver, 58% copper, which at equilibrium consists of alpha and beta phases having mass fraction of W of alpha is 60% and the mass fraction of beta is 40%. If so, what will be the approximate temperature of the alloy? If such an alloy is not possible, explain the reason. Well, so we have got a composition of, say, 50% silver and 50% of copper, which is right here. This is the composition, or CO. And then we want to see if it is possible to have 60% of alpha and what is left, which is 40% of beta phase in the solid form. The solid form of alpha and beta is resulted in this region, right? In this actually region of the phase diagram down here. In order to see whether this is possible to get mass fractions of 60 and 40 of alpha and beta, what to do is to compute the two extremities. First, we move on to the upper limit right here. Upper limit is right here, and the lower limit is the room temperature or above room temperature, somewhere here. What we need to do is to see what proportions of alpha and beta do we get in the two extremities, and if the proportion in question lies somewhere between the two extremities, then we can say that yes, it is possible to have this much of, say, alpha and beta, and then we will investigate to see at which temperature it will be resulted. So let's do it for the first extremity, which is just above or just below eutectic temperature. In order to do that, what we need to do is to write down what we have got. We have got an overall composition of 58% of silver, and we are after a composition when we have got 60% of alpha and 40% of beta. What we need to do is to write to use the lever rule, and when we make use of the lever rule for this temperature just below TE right here, we will have a number of numbers that are already given, number of values that are given, and those include, say, this value, which is composition of beta at eutectic temperature, just below eutectic temperature, and then, not this one, and then we have got the overall composition, which is right here, CO, and then we will have also another composition, which is, say, a C alpha composition, that is the solubility, maximum solubility of beta in alpha indeed. So these figures, we take them out and we substitute these values into the equation. So we have got C of beta, which is equal to 91.2. We have got overall composition, which is 0.5 or 50% indeed. We have got actually, again, C beta, which is 91.2, and we have got C of alpha, which is 8, taking out all these figures from the phase diagram and substituting all these values. It's giving us 50% of alpha is resulted just below TE, and of course what is left is the other phase, which is beta, and 50% alpha and 50% of beta is resulted just below TE. Now let's do the same down here at the temperature, which is I would say at room temperature, which is 200 degrees C, above room temperature, but anyway, it is very low, where there will be no further changes if we lower it to room temperature. If we apply the lever rule again down here, let's see what happens. Now, down here, as you can see, the solubility limit decreases. So the solubility limit of beta in alpha decreases and it reaches to 0. Same to the other side. The solubility limit of alpha in beta decreases and it reaches to 100% of beta and 0% of alpha at room temperature. So if we substitute the values of 100 for beta, again 50 for overall composition, and for alpha this time it is down to 0. Then we get 50% of alpha again at this temperature of 200, or even at the room temperature we get the same value. So 50% of alpha, and of course what is left is remaining 50%, which is beta. So we moved from the top to the bottom of this region, and at both extremities we have 50% alpha and 50% of beta. What it means is that never in between we can get 60% of alpha and 40% of beta. All the way from up here to down here, we always had 50% of each of the two phases. So what is asked in the statement of the question, we can say that such a composition is impossible. Okay, let's move on to the next problem. Well, here we have got a eutectic phase diagram. We have got 500 grams of 98% of silver. Let's see where it is, 98% of silver. Right here. This is an indication when we have got 98% of silver and 10% copper. This is slowly cooled down from 100,000 degrees C to just below eutectic isotherm line. So starting from this temperature right here, it moves down to a point which is just below TE right here. In doing this, we want to see in A, how many grams of liquid and proeutectoid beta are present at 850 degrees C. Where is 850 degrees C? Point B. If we project it to the vertical axis on the left, that's where it is. So it comes to 850. We want to see how many grams of liquid and proeutectic beta we will have at this temperature. Let's move on to the next slide. In this slide, we have just a fraction, an enlarged section of the previous phase diagram. Now we can better see what is happening. So starting from 100 degrees C, which is point A, we lower it to 850, which is right here. Okay, at this point, what we need to do is to draw a horizontal tie line right here, and where it intersects with the solid use line on the right, we project it down and we get this value of 95. Similarly, to the left, the intersection of the tie line at this temperature with liquidus line, we project it down and it gives us a different composition, which is 86. Now we have got, indeed, we can find the length of the tie line. Well, in the middle, somewhere here, we have got the overall composition of 90%. And to the left and to the right, we have got 95 and 86. So we can easily compute the length of each portion of the tie line and the total length of it by making use of these figures and apply the lever rule. In order to see how much of liquid we have got, it's very obvious that this point is closer to the liquidus line than to the solid use line. So we are expecting to have more liquid in it. Now let's apply the lever rule. In order to apply the lever rule, we write the equation, this equation here. What is this equation? This equation is dividing the length of S, which is the longer portion of the tie line, to total length, which is R plus S. How do we get the lengths? By making use of these numbers down here. So 95 minus 86 gives us total length, that is written down here, total length of the tie line, and the S portion of it can be resulted if we compute the value of 95, which is this point, minus this point, which is 90. We substitute these values into the equation, and then it gives us the weight fraction of the liquid phase in this at this temperature for this given composition, and that is 55%. We know that we have 500% of 500 grams of the material at hand. That was mentioned in the statement of the problem. So multiplying 55% by the mass of the material, it gives us the weight of the, say, liquid phase, and that is 275 grams. And of course, what is left is the solid phase, and we don't really need to have it computed, but if we want, we can just apply the same principles. This time, we will be dividing the shorter portion of the tie line by the total length. So R divided by R plus S, which is giving us 45%, and multiplied by 500 grams, it gives us 225 grams of solid phase, which is proeutectoid site for this given example. Okay, now let's move to part B. How many grams of liquid and proeutectic beta are present just above the eutectic? Well, just above the eutectic, as we see, this is eutectic. Just above is somewhere here. So what we need to do is to drop the temperature again down, and just above it, apply the tie line, the same as what it happened at this previous point. So we bring it down to just above and apply the tie line. And as we can see, if we apply the tie line exactly the same as what it was, we get the use of the amount of liquid and also beta solid. of course, this time this point is closer to the solid region than single phase solid region than single phase liquid region. So we are expecting to have a lot more solid phase than the liquid phase in it. And when we do the computation, the same as what we did, we end up in only 30 grams of liquid phase and 450 grams of the solid phase, which is beta solid, and that is reasonable. And then in part C and D, which I have mixed together, it's asking us how many grams of alpha and beta phases are present in the eutectic structure just below the eutectic isotherm line. Again, this is the eutectic isotherm line, this one. Just below, we draw the tie line. Then we have the limits of 91.28 and also overall composition, which is 90. And we apply the say Thailand. Indeed, this point is a little misplaced. It should have been just on this line, which is right here. So it is just slightly misplaced. If we apply the Thailand as it happened in down here, then we get the values of, say, two phases of alpha and beta. Because just below this, we will have only alpha and beta present. There will be no more liquid present. And then we can just compute the values of alpha and beta. It's very obvious that this point is close to beta phase compared to alpha phase. So there is a lot more beta at this point, at this temperature, than alpha. So what we get, if we apply the Thailand the same as what we did, we end up in only 7% of alpha, and what is left is 493 grams of beta phase, which is reasonable because this point is closer to beta and we will have a lot more beta than alpha. Okay. Is there any questions? Okay. If there is no more question, then we will continue with the presentation, with the Tute session, and we go to the, say, next problem. Problem 3, phase equilibria. For a 99.6 weight percent of iron and 0.4% of carbon at a temperature just below eutectoid, determine the following. In A, composition of Fe3C, which is also referred to as cementite, and also it is known as iron carbide. So it has got so many names. So composition of cementite and ferrite. Alpha stands for ferrite. Ferrite is the soft phase and cementite is the hard phase. So how many grams of each? What is the composition? At A, what is the composition of cementite and ferrite? And then in B, amount of carbide, which is also cementite, in grams that forms per 100 grams of steel, and in C, the amount of perlite and protectoid ferrite. Let's see how we will do this problems. First, we've got to take a look at the phase diagram for this problem. This is the phase diagram that is used for production of steels and cast irons. To the left, we have got 100% of ferrite, of iron, which is also referred to as ferrite, and to the right, we have got 100% of cementite, Fe3C, which requires 6.7% of carbon. So where we have got 6.7% of carbon, then we will have 100% of cementite. We don't need to extend it to 100% of carbon because there is no industrial use of any more carbon content. This is the only portion that is needed, which is just the portion of the complete iron carbon phase diagram. Okay, now we want to see what is the composition of cementite and ferrite. For this given composition, when we have got only 0.4% of weight percent of carbon, we will have a maximum solubility of cementite in ferrite, or carbon in ferrite, indeed, a maximum solubility of carbon in ferrite, which comes to 0.022% of carbon right here. right here, let me just take the laser. Okay, right here at this point, at the temperature of 7 to 7 degrees C, there is maximum solubility of carbon in ferrite. So it comes to 0.022 weight percent of carbon. In this region, which is the sky blue, we have alpha ion, which is also referred to as ferrite. And then the overall composition for the material given is 0.4% right here. And we also know that the composition of cementite, this one, it has 6.7% of carbon. Okay, and in part B, the amount of carbide, which is also referred to as cementite or Fe3C in grams, that forms per 100 gram of steel. Excuse me. Well, for doing this part of the problem, what we need to do is to apply the lever rule and draw the tie line as we did before in the previous problems. And for doing this, we draw this tie line right here, and then we substitute the values and multiply the values by 100%, 100 grams of the material that is initially given. So in order to apply the lever rule right here, we've got to be able to compute the overall length of the tie line starting from 0.022 going all the way to 6.7. So the difference between the two figures, which is 6.7 minus 0.022 gives us the overall length of the tie line. And then we've got to compute the length of the line from the R portion of it and also the S portion of it. As we have the figures of 6.7 indicating the end of the line, up to composition CO, which is 0.4, and up to this point, which is 0.022, we can easily compute the S portion and R portion of the tie line. And then, in order to compute the amount of cementite, which is right here, we've got to apply the R portion of it, which is the far side of the tie line. Dividing R by overall length gives us the amount of cementite. How do we compute it? So the length of R is 0.4 minus 0.022, and we write it here. So dividing this smaller portion by the overall length gives us the amount of cementite, and that is 5.7 grams if the whole result is multiplied by the mass of the material, that is 100 grams. So it gives us this much of cementite. What is left is, of course, the other entity, which is ferrite. Taking 5.7 out of 100 grams leaves us this much of alpha, which is ferrite. Ferrite is the soft phase and cementite is the hard phase. Moving to the next part, the amount of pearlite and protectoid ferrite. Note, the amount of pearlite is equal to the amount of gamma ion, just above Te. This Te refers to eutectoid temperature, which is 7 to 7 degrees C, right here. In order to compute pearlite is formed down here, somewhere here. Down here. In order to do the computation of pearlite, if we can compute the amount of gamma ion, then it is equal to the amount of, say, pearlite. In order to understand this, you need to read the lecture material and watch the review of phase diagrams, which I have recorded and uploaded on the Blackboard site. Well, anyway, for this given composition of 0.4%, we've got to apply the tie line. However, as it was mentioned, we need to compute the amount of, if we compute the amount of gamma ion, then we can easily find the amount of pearlite that is produced. So this time we apply the tie line just above Te. This is the region when we have still gamma is still in place. Now we have to compute the total length. We know that this point has got a composition of 0.76, where we have got 100% of pearlite, right this point. And maximum solubility of carbon in ferrite is 0.022, and overall composition is also 0.4. So we can easily compute the total length of the tie line and each portion of it, S and R. So applying the lever rule as it happened before, we can compute the amount of perlite. The amount of perlite is equal to the amount of gamma. Up here, if we divide R by total length, it gives us the amount of gamma, and that is equal to the amount of perlite. And for computation of the amount of ferrite, we've got to divide S portion of the tie line by the total length. So having it computed this way, we end up in 51.2% of perlite, and what is left is, of course, ferrite, which is the other entity. Okay, any questions on this? Okay, no question. Then we will continue with the problems, moving on to the last problem, and that is this one. What is the carbon concentration of an iron carbon alloy for which the fraction of total ferrite is 0.94? Well, in order to do this problem, we've got to make use of the lever rule, and this time we have the amount of the material or alpha phase available. So if we say apply the lever rule, we can easily compute the amount of the carbon concentration, and that is this way. If we know the amount of the phase in question, which is alpha, and that is equal to 0.94, which is ferrite, we have got 0.94% of ferrite. Then we apply the lever rule in order to see how much, what is the overall composition. Well, in this equation here, the carbon content of Fe3C, it's very obvious. It's 6.7%, which is at the right extremity, right here. The amount of alpha is also given for ferrite. Maximum solubility of carbon in ferrite is also something that we know. And overall composition is something that we are after, which is CO. So we are after CO. We have got the values of concentration of carbon in cementite and also in ferrite. If we substitute the other three values, having 0.94 at hand, we can easily work out the value of overall composition, and that comes to 0.42 weight% of carbon. So for this overall composition or concentration of carbon in the steel, we can have this much of ferrite. Okay. Thank you very much, and this concludes today's Tute session. Please practice on all of the problems that we worked. When you take a look at the solution, go over it. It's easy to understand it. When you do it yourself, then it's the time when you face questions and problems. However, you have time. You have got the solutions uploaded on the Blackboard site, so you can easily find out what you did right and wrong. And if there is any question, please get in touch with me and ask your questions. Thank you very much, and that's all for this session.